Alright, hello again everybody. It is raining outside right now, so you may hear that in the background. I apologize for any sounds you may hear. Still stuck at home. Probably stuck at home for the rest of the semester. Apologize, maybe losing my voice soon. Recording a lot of lectures lately. Alright, so let's go over section 7.2. I had a video for this that was originally in the queue with your other videos, but it was not appropriate, or I can't remember why I took it down for some reason. Maybe there was a part of the section that was wrong. So I'm reposting this. This is actually from home, so this is a new one. All my other videos are like from 4 years ago, but for college algebra, we need 7.2 we're covering this week, so I'm going to put that up as soon as I finish this. So, all right. So we're going to talk about 7.2, applications of exponential functions, models of population growth, compound interest, and the number e. So e is a number. Just use a letter to hold its place, kind of like pi. So population growth, population can refer to a bacteria in a laboratory, wildlife in biology, or many other living things. For example, maybe a virus spreading in a population could be a population growth of some kind. Might be relevant. The growth of a population depends on a large extension of the number of members of the population capable of producing more members, i.e. if a virus affected other people. Exponential models are often good fits for these situations. So we'll be looking at population models of exponential growth with no limiting factors. Limiting factors is for another day, another class. Population will frequently grow according to the equation Pt equals P sub 0, so that's the initial population, and then you have some kind of growth factor to the t power. So we use the following notation where Pt is population times t, P sub 0 is initial population times 0, t is the variable representing time, and that could be in minutes, it could be in seconds, it could be in hours, it could be in days, it could be years. Make sure you read the question correctly and know what they want their answer in. The larger A is, the faster the population will grow. If A is less than 1, the population is shrinking. Biologist is culturing bacteria in a large petri dish. She begins with 1,000 bacteria and supplies sufficient food for the population to double every hour. Find a function that models the growth of this bacterial culture. So basically, we're in the form P of t equals P sub 0 of A to the t power. So we said the initial would be 1,000 bacteria, and we said it would double. So that's going to be 2. A is going to be 2. It's going to double every hour. Now, I'm going to leave that as t because that's our variable, t. And if we want to check to make sure this is true, we could say let t equals 1, and what should happen? In 1 hour, it should double. So we should get 1,000 to the first power, which is going to be 2,000, which is twice of what we started with, 1,000. So that's the model we're going to use right there. A biologist is, once again, same question, but part B, determine the population when it reaches 16,000 bacteria. So once again, we're going to write down our equation that we found. P sub 0, actually that's 1,000 now. We said it was 1,000. And 2 to the t power. And then so once we have this, we're going to say, well, we have 16,000 bacteria. We want to know when that happened. So we're going to be solving for t. Now, later on in 7.3 and 7.4, 7.5, we discover ways of solving this when we don't have like bases. We'll see that we'll have like bases in a moment. We divide both sides by 1,000. And you'll be doing that for those problems. But right now, we're going to get a nice power of 2. And you can see that it's 16. And we can solve this now. Later on, these are different bases. We could be able to do that. Our powers of 2. So that'll be 2 to the 4th for 16 equals 2 to the t. So remember, it's like canceling. If our bases are identical, our exponents have to be equal. So it's kind of like canceling our bases. Not really. But we're going to get 4 equals t is our answer. So in 4 hours, alright, so now they said they have 1,000 bacteria. Once again, calculate the population 2.5 hours after the scientists began. So now we're going to have our same formula that we came up with before. Write that down. And then once we have this, we're going to say, well, what is when we put 2.5 hours or 2.5 in here? And so that's going to be 2 to the 2.5. And you're going to need your calculator to that, because when you're raising an exponent to a number, that's not an integer, you're going to have to, it's going to be irrational, and you're going to have to use your calculator for that. So I'm going to use this calculator because it shows up better. It's my wife's. As you can see, it's pink, but the screen's backlit, so you can see it a lot better. So I'm going to say we have 1,000. Actually, I did it earlier before. Let's clear the screen. 1,000, and we're going to say that's times 2 raised to the, and let you know you're in an exponential spot, but sometimes it doesn't do that if you don't have a really nice calculator. 2.5, and then we close out our parentheses, oops, down here, and we're going to get 5,600, focus, you'll read that, 5,656. I need a nicer calculator like this, especially if I'm going to keep teaching from home. Once again, if you all need any help with any of the lectures or need me to clarify anything, if it's something that can't be said in a short email or clarified in an email, you can contact me. I can even make a video response if you'd like me to. I just need more than 24 hours notice on that. So now we're going to talk about simple interest. So we model our own population growth given with the correct information, but now we're going to talk about interest. So this is a big deal in banking and a lot of other things. The interest equals principal times rate times time, which applies to simple interest. So that's just simple interest. I is the interest earned, P is the principal, R is the annual interest rate as a decimal, and T is the time in years. So the total time is we have principal plus interest. Well, interest was PRT, so that's principal times rate times time. We factor the P out and we get P times 1 plus RT. Now, why would we factor it out? Because if we apply it in multiple units of time, every time investment is compounded and added to the interest earned. So you earn interest on your interest when they compound it. If they compound it annually, that means that every time they do it, they're going to multiply it again by 1 plus R. And then so basically what happens, you get 1 plus R squared, and that becomes our time T. And so you keep doing this after T years, you're going to get P times 1 plus R to the T power invested. So now every year, they may not compound it at the beginning of every year. Some banks compound it daily, weekly, monthly. Usually it's monthly. Some places are semi-annually. But it's compounded n times a year. Interest compounding is compounding period and compounding times per every year. The interest rate is going to be split up between those times it's compounded because it's a nth unit of an entire year. Because if I add all these together, I should get R back out, and I added n times, my n's would cancel. And so first, just R, 2 is R over 2, quarterly, R over 4, monthly, R over 12. And then you can get, weekly, you could get weekly, you could get daily, hourly, minutely. Then it gets kind of ridiculous. And if you're going to keep going, we'll talk about E here in a second. So every time compounding period principal is multiplied by 1 plus R over N. We do that n times for every year. So after T years, we multiply by T. So N to the T is going to give us 1 plus R to the N T. And once again, this is just our interest that we're compounding over and over and over again. We multiply it by a principal, we'll get the entire amount, A. So Sandy decides to invest $10,000 in a savings account, earning 4.5% interest annually, compounded quarterly. So that's 4 times. So let's write that down. So the rate is going to equal 0.04. Remember, it's percentage. If you do 4.5 as a rate, that means it's 450%. That's insane. You'll notice that when you get answers out on your calculator, they're enormously bigger than the number by a factor of 10, 100, especially a factor of 100, bigger than what you should be getting or what you think you should be getting. Go back and make sure you put your rate in decimals and not in percents into your calculator. 10,000 was our principal, and then compounded quarterly. Quarterly means N is 4 times. And what would be the value of investment after 3.5 years? So we're going to use the formula PT equals P1 plus R over N to the TN, or NT, either way is fine. And so I'm going to start substituting it. So I'm going to have 10,000, and we have 1 plus, and then my rate, which is 0.045. Remember that decimal, not in percent. 4, and then I'm going to have 4 up here to the T, And then now they'll want us to plug in 3.5 years. So we're going to say P of 3.5 equals, not 1,000, 10,000, excuse me. 1 plus 0.0454 times 4 times 3.5. Should just use parentheses. All right, so once again, this is a calculator exercise. You have to make sure you put it in your calculator correctly. And so we're going to have 10,000. And then we'll put parentheses 1 plus. And then we're going to do another parentheses for the rate over the number of times compounded, 4. And close that up. And then we're going to raise this all to the 4 times. Now, here's what you have to be careful. If you don't have a really nice calculator like this, you want to make sure you, let me go back. Put this numerator in parentheses, because if you don't, the exponent and parentheses, because if you don't, you're going to get this whole thing raised to the fourth power, and then the whole thing times by 3 instead of the exponent times by 3.5. So you want to make sure that that is the exponent, so you're going to have to put that in parentheses. This is a really nice calculator. It knows to do that. It keeps it like that. Actually, I should go back and put another parentheses at the end of this. Automatically knows I want to insert it. That's very nice. Like I said, my calculator's a lot nicer than mine. But yeah, I do it so y'all can hopefully see it better. Focus. Focus. Doesn't want to focus. Oh, y'all get the idea. All right, so we enter that, and we're going to get, you focus better down here. I don't know if y'all can read it that far away. That's going to give us 11, 609.551, and it's 518. It's 0.518, so we're going to round that up. I'm going to say 0.2 because we round it off the nearest cent. Is what you usually do when you're talking about these amounts. Of course, it's in dollars. All right, and so next we talk about the number e. So if we were to keep compounding forever, at every instant, every time, so what happens if we compound more and more frequently so n becomes very large? Let's do some calculations. So we have 1,000, r equals 1, t equals 1. We can see that these numbers are approaching a specific value. The value is so important, it has its own name called the natural number e. So in other words, this value e is super important to math, and it's sad that some students only see it once or twice in a class, in a math class in their life, but e in higher level math is such a great number. But this is one of the ways we explain how to find it, or where it pops up everywhere, kind of like pi. The formula for the value of an investment p at $t compounded continuously will have this formula where if we keep compounding, we're going to get 1 time is 2, 4 times a year is 2.4, 12 times is 2.6, and then every day is 2.7. So we're getting about a percent increase, or 0.1%, which can be a lot if you're dealing with a lot of money. But once you get to 1,000, 10,000, a million, you're not changing anything until you get to right here. So this number right here, this becomes close to e. This approaches e. And so e is a set value in your calculator. And so you hit second function, and I'm going to say e to the first power, and you see it's 2.718281828, and it seems like it has a pattern. It doesn't, and keeps going on forever. It never repeats itself, but it has a repeating portion right at the beginning, or it looks like it has a repeating portion right at the beginning. So from exercise 2, we do the same investment, but now she's going to say compounding continuously. So instead of the old formula, we're going to use p equals, and then p to the ERT. And so this is going to be rate, this is time, e is your natural number, p is your initial amount, p sub 0. And some people remember this as being the word pert. It was a shampoo that people used a long time ago. I don't know if it's still relevant. Some of y'all may never heard of it before. But they call it pert. And so we're going to say she had 10,000 in our example, and she's going to multiply it by e to the r. And once again, your rate is 0.45, and then you multiply that by t, whatever t is in t in this case. So let me just write the formula first. And then we're going to say we'll plug in 3.5 like we did last time. And that's going to be 10,000 e to the 0.045 times 3.5. Let's plug that into our calculator. We get second function e. We need 10,000 first. then we have a second function e to the 0.045 times, like I said, I have a nice calculator, so I don't have to worry about making sure I'm still in the exponent here, but you're going to have to put parentheses around it normally in order to get that to happen, like I did right here. And then you hit enter, and it says we get 11,705.8, and then it says 07. I'm going to round that to 181. Once again, this is dollars, round to the nearest cent if you can. And then it says, in the last part of this example, it says how much more is this amount than $695.52 like we got last time. And so we're going to say we have our amount we found earlier, 81 minus off 11,659.52, and we're going to see the difference between these two numbers is going to be, so carry the 1, that's going to be 9, that's going to be 2, and we get the 5s cancel, and then we're going to get these cancel, and so I'm going to borrow 1 from here, that's 10, and that's going to be 1, so it's $10.29. So compounding quarterly in this amount to compounding every second of every instance you could possibly, the fastest you could possibly compound it continuously, you'd only get $10 more. $10 more over a 3-year investment, not a lot of money. $10, I mean, that minor amount over a very large amount of money, like millions of dollars over 20, 30, 40 years, it can add up to another $1 million, or a significant fraction of $1 million, in a given amount of time, depending on your rate. But yeah, so you need to be careful about, how many times compounding a year. It can make a big difference for large amounts. For very small amounts, you're not going to see much change. So that is 7.2 college algebra class. Hope you all have a great day.